Press start, and then I hide this so it's not in your way, and you can
we're ready to go.
We're ready to go. I'd just like to make an announcement,
Okay. Do that.
which is to remind you that next Tuesday you are meant to go and see Daniel Jurgen at 10 o'clock in the morning. If you can possibly make that one, that's the one with especially for the students, and they're anxious to get it well populated. So bring all your friends. And we'll pass around a attendance sheet because I want to make sure that people from my class show up. If you're not there in the morning, can you go in the afternoon? That would be great. And that's the end of my announcements, I guess. And I'm thrilled today to have Dr. Denning here to talk to us about nuclear. He's like the expert. And so I'm just going to get out of the way and let him go.
Well, thank you. Okay. So I'm Rich Denning. I spent most of my career at Battelle Memorial Institute just down the road, working in the area of reactor safety and reactor risk assessment. I've been involved with the two major NRC programs, Nuclear Regulatory Commission risk assessments that were performed in 1975 and 1990. And I've been on the Department of Energy's Advisory Committee for Nuclear Facility Safety and the Nuclear Regulatory Commission's Advisory Committee for Reactor Safeguards. And I joined the faculty here in 1999 and actually was continuing to work with Battelle at that time. So I'm going to talk about nuclear energy and the need for it. And the title is actually Saving the Global Environment, the Role of Nuclear Energy. The status of nuclear power today is that we have 104 nuclear power plants operating, represent 20% of the electricity in the United States. Almost all of the plants have either applied or received a extension from 40 years lifetime to 60-year lifetime. A lot of the plants have gone through power uprates. When these plants were designed, their intended capacity factor, that is the fraction of time that they would be online producing electricity, was 85%. The rest of the time they're down for refueling or for scheduled maintenance. And in the early days, when we had lots of material problems with the nuclear power plants when they were just starting up, the capacity factors were averaging about 55%. Today they average around 90% because basically the kinks have been worked out. And what they've done is they've extended the time period between refuelings in nuclear plants. So instead of refueling every year, they refuel either every year and a half or every 2 years. So it really is a mature technology. There are 4 new nuclear power plants that are under construction today in the South. They are all called AP1000s. They're actually 1,200 megawatt electric plants, and they are passively safe. There's new philosophy in the design of reactors where we reduce reliance on AC power, and the AP1000 plants designed by Westinghouse are passively safe. And in this competition for new reactors in the United States, Westinghouse has really been the winner. General Electric has a version, Areva, a French company, has a version, and they're building plants in Finland and in France of a new design, this what we call Generation 3+ design, that truly are safer. I'm not saying that current plants aren't safe, but taking into account all of the experience we've had, there are these safer plants. The thing that's really hot at the moment is small modular reactors, and mPower, a company that was made from Babcock and Wilcox and other organizations, is just got a contract from the Department of Energy for the production of for the design of a small modular reactor. I'll explain why small modular reactors are so hot in a minute. And TVA, Tennessee Valley Authority, has a commitment to construct a small modular reactor of the mPower design on their site. There are 18 license applications that have been submitted to the NRC, but right now, other than the 4 reactors that are being built right now and the work on SMRs, everything else is stalled. And the reason it's stalled is a couple of reasons. Probably the most important is the very low cost of natural gas today. And in the lower right-hand side of this, you see this curve here, and that shows you historically historically the cost of natural gas has fluctuated dramatically, but over the last few years, what you see is it's dropped dramatically in the United States, and that represents a boon for the utilities in that you can build a gas-fired power plant really quickly, and with the cost of natural gas this low, there's nothing else you do in the United States. This happens to be the European price of natural gas today, and so I talked to utility executives. What they think is going to happen is that as soon as we've really developed the capacity to really export LNG, liquefy and export the natural gas, what's going to happen is we're going to see this migrate back up to the global world price of natural gas. But today it's low, and certainly for a few years it'll be low. How much natural gas there is, what kind of problems we're going to have with fracking, we just don't know today. We do know, of course, that is a greenhouse gas producing fuel. It's half as bad as coal. It's like telling your doctor you went from 2 packs a day to 1 pack a day. But it obviously it's better than coal in that regard. There is a question as what's the best use of natural gas. If you're going to burn it, should you burn it in the houses and directly get that energy, or do you go through converting it into electricity where you have a loss of efficiency and then you use it and have another loss of efficiency? So there's a question also how you should use that. The nuclear power plants today in the United States will all undergo some upgrades related to Fukushima. What happened at Fukushima really, directly what happened at Fukushima really doesn't have much relationship to our nuclear power plants. That event, as it was, would not have happened in the United States with our plant designs. Of course, really, and I don't want to get too much into Fukushima right now. We may talk about that later if you have questions. But there are going to be some substantial things that are going to be done to U.S. nuclear power plants to further reduce the risk of things like Fukushima. And so the utilities are faced with some fairly significant upgrade costs to their plants. The big problem right now with selling new nuclear plants, there are actually kind of two things. But the biggest thing is the large upfront cost of a large nuclear power plant. I'm going to talk about nuclear power plant economics later, and they are definitely competitive, particularly with loan guarantees, and I'll tell you why loan guarantees are important. But right now, since it costs $5 billion for a plant, the utilities just don't have that much money. They have to borrow it. It represents a very significant fraction of their total capital value, because we have a lot of small utilities in the United States as opposed to places like France where there's a big utility, stuff like that. And then the other thing is this lack of a geologic waste site. To the public, we so often hear the concern about lack of geologic waste site. I'll talk about that issue and whether it's real or not. Okay, now we're going to go to some real basics about everybody that isn't already a nuclear engineer is going to come out of this a nuclear engineer. So uranium, there are two isotopes, two kinds of isotopes that occur naturally. One is uranium-238. That represents 99.3% of the uranium, and it is not fissionable in a reactor. It's the uranium-235, which is only 0.7% of natural uranium that's fissionable. Fission occurs in this manner. You have a neutron that bangs into a uranium-235 atom. It temporarily forms an intermediate state, and then it fissions typically into two fission products. And those fission products actually, reactor safety is all related to fission products in two respects. The fission products are radioactive. I won't explain exactly why. There are reasons why they're radioactive. But that means that they will decay with time, and as they decay, they release energy and into other isotopes. Okay, so they're radioactive, and it's the release of those fission products that really represents the hazard of a nuclear power plant accident. That the fission products get out of the fuel somehow into the environment and into the body or expose the body. The other part of it is that because they release heat, when you shut down your reactor, you still have this radioactive decay going on. So that we have what we call decay heat that you have to deal with when you shut the reactor down. So when we scram our reactor, when we really shut it down, what happens is that the power drops very rapidly, but it only drops down to about a few percent of the initial operating power, and then it decays away with time. But that few percent of the initial operating power is still an awful lot of energy that has to be released. And that's why we have emergency core cooling systems that flood a reactor with water to make sure it doesn't melt down due to this radioactive decay heat. So that's what reactor safety is really about, is containing those fission products. One of the products of this also is neutrons, and this guy, my cat is going to be so disappointed. But I have another one. So anyway, we also produce neutrons, and on average we produce about 2.5 neutrons for every 2.5 neutrons. There's 3 shown there for every fission. And those neutrons then are going to go on and cause the chain reaction. Now, the thing that's so dramatically different about nuclear energy than atomic energy, I mean, people think about atomic energy and they use that name wrong when they really mean nuclear energy. But atomic energy, if you really think about the energy that comes from doing things with electrons and having chemical reactions like burning coal, burning natural gas, the amount of energy that's released is in the area of electron volts. That's just the form, a nomenclature we have for energy. In a fission reaction, we have a release of 200 million electron volts. So basically, you have 10 to the 8th more energy released per reaction than you do when you like burn coal. So that's why it's such a concentrated form of energy, and why the footprint of a nuclear power plant is really so small relative to the footprint of other energy sources. Okay, then the chain reaction is when, on average, one of the neutrons that produced goes on to cause one more fission, then we have a chain reaction, and we can, as we work with a nuclear power plant, we can have that chain reaction occurring at any population of neutrons that we want, at any energy output that we want. So we can, so we have, when it's an exact balance, we call it critical. That is, for every fission that's occurring, one neutron goes on to cause another fission. That's called critical. If we make it supercritical, then the number of neutrons in that reactor that are flying around and causing fissions increases. And if we make it subcritical, then the number of neutrons flying around decreases. So this is a very conceptual version of a nuclear power plant. We see here what is kind of a containment building. Containment building doesn't look exactly like that. It's much bigger. Here's a reactor vessel, which is much smaller. And so inside this we have water, and here's our fuel. Okay? These are called control rods, and what the control rods are is, we call them a neutron poison. What they do is they're a big absorber of neutrons. So in this case, we have our control out of the reactor, and so it's producing heat, and that's why we have all these bubbles here. And then over here, we've inserted that poison. It's made it subcritical, and so you can see we have a few bubbles. So that's the way we control this being subcritical, critical, and supercritical. And as I said before, we can allow the power to go up to any level we want in here and then stop it and make it critical, have it stay at that level. So that's how we operate a nuclear power plant.
What materials are the control rods made out of?
Boron typically can also be silver, indium, cadmium. Cadmium's a strong absorber. Boron are strong absorbers. So how do we produce electricity? Well, the way we do it is we have heat. We have a pot of water, we boil the water, it turns the turbine, the pinwheel, turns the generator, and we get electricity. That's the way it's done in a nuclear power plant. That's also the way it's done in a coal-fired power plant for engineers. We do this using the Rankine cycle for light water reactors. There are other cycles that different kinds of reactors use. There are two kinds of light water reactors operated in the United States: pressurized water reactors and boiling water reactors. This is very conceptually, again, a pressurized water reactor. Again, you see this containment building around here. That's the final barrier to the release of radionuclides. Here's the core. Here are control rods coming in from the top. Here's water flowing. Doesn't show very well here. Flows up through the core, takes the heat away, and then the hot water goes here into the steam generator. This is operated at high pressure, 2,200 pounds per square inch, so that even though the temperature is very hot here, the water doesn't boil in a pressurized water reactor. The hot water goes over here into a steam generator. This is at a lower pressure, so over here the water boils, steam goes, turns the turbine, generator, we condense it, pump it back around this way, this cold water gets pumped around there. So that's the way a pressurized water reactor works to produce electricity. Boiling water reactor doesn't have a steam generator. You actually boil in the core, and and this steam then goes directly out to turn the turbine, and then comes back in this way. So we call this the boiling water a direct cycle, and the pressurized water reactor is an indirect cycle. This is a nuclear fuel cycle. I just want to show you some parts of this because I'm going to talk about some aspects of the fuel cycle. First, we have mining, concentration, conversion to uranium hexafluoride. I'm going to go through this again. Then we have to enrich it. We have to take this natural uranium, which is 0.7%, and enrich it so the uranium is like 4% to 5% U-235. Then we have to make our fuel. We go down here, we have the reactor, and then then we store it, and hopefully someday we dispose of it. But there are other options. In Japan and France, they actually recycle this, and they take the plutonium out, make MOX fuel, mixed oxide fuel, and they continue to cycle it around here. Okay? But as far as the United States is concerned, we have just this once-through system where eventually we would do this. Yeah.
On the new generators, are we still doing
Yes,
that?
we're still
We're
doing
not gonna
that in the
recycle?
United States for two reasons. Originally, the reason that we didn't go to MOX fuel, we do actually have some mixed oxide fuel that's come from demilitarization, where we've taken plutonium out of weapons as part of an agreement with the Russians. And that plutonium is going into mixed oxide fuel, but it's not really the recycling of light water reactor fuel. The reason we haven't recycled the light water reactor fuel is, first of all, uranium is still inexpensive, so it's not economically a thing to do. But the reason that the country kind of took a policy not to do it was in the Carter era related to proliferation. Because your ability to reprocess fuel could potentially give you the capability to make a plutonium weapon. Not that anybody would make a plutonium weapon out of reactor fuel. There are reasons I won't bother to get into here. But what happens is you build up isotopes in the plutonium. You burn this up enough so that you get some isotopes in the plutonium that make it very difficult to make a controllable weapon. That's all you need to know about weapons. Now, maybe I'll talk a little bit more.
Business of recycling, though, that's not a breeder reactor, right?
No, that's not a breeder reactor. This is still what we call a converter because the conversion ratio is less than 1. In a breeder reactor, indeed, you can go and you can produce as much plutonium as you burn up and really make full use of that uranium resource that's out there that we only take partial use of today.
I'm assuming that even on the recycled one, there's still some sort of waste that they need to.
At the end, there is waste.
What's like the percentage difference of
waste?
How much they actually get to recycle?
At the moment, what they recycle is just the plutonium. Okay, so that you're left with a lot of that waste that otherwise is important as far as a repository. There's work that's gone on in the last 10 years. DOE is not too big on this at the moment, but it is potentially important where you can have a burner reactor in which you can take the stuff that's really the long-lived isotopes and you can recycle them back through a burner reactor so that you really dramatically decrease the amount of long-term stuff that goes into a waste disposal site. So if you look today at the way, what would happen, so if you look at a waste disposal, geologic waste disposal site, and you compare it with uranium ore, okay, the way we would do it today, if we did it at Yucca Mountain, it would be like 100,000 years before that would look like the equivalent of uranium ore as far as the amount of radioisotopes, concentrations there. But if you do a burner reactor and burn up those long-lived stuff, you can actually reduce that to about 1,000 years, which is certainly, now the reality is neither one of them really represents a true hazard to the environment. So I'm not sure that it, but politically, it's more attractive. Okay. So I'm going to go through some of the steps here. The reason I'm showing the mining and milling is because this is one area where I think that you have the potential for some environmental contamination if you don't do it right. I think most of these areas, the risks get dramatically overplayed, and I'll give you some feelings to what the risks are. Basically what happens here is that you're taking uranium ore, you're concentrating it. Yellowcake is the form of when you purify U3O8. U3O8 is the stable form of uranium dioxide. Any uranium out there eventually will form U3O8, and we call that yellowcake because guess what? It looks yellow. But we do things like in situ leaching now, and there's some concern about chemicals and that kind of stuff. Historically, in the weapons development program, there were some major mistakes made in the treatment of this uranium ore, where they take the uranium ore and they have what they call tailings, is what's left over from the ore. And people actually took some of those tailings and they used it for landfill in areas. And because it has a fair amount of uranium in it, it's pretty radioactive. And so then when they figured out what happened, they had to go and take that away and all this kind of stuff. So one of the things you definitely have to do is you have to control those tailings, and you have to cover them because they're always producing radon gas, like the radon gas in your cellar that comes from uranium in the ground. Okay. So we have U3O8. We then have to convert it to uranium hexafluoride, which is a gas. And then we have to enrich it, and we used to enrich it using a process called the diffusion process. There were 3 diffusion plants, gaseous diffusion plants in the United States, one at Portsmouth, really in Piketon, Ohio. And that's now shut down, and it's being converted to a centrifuge enrichment. Here are centrifuges. They swirl around like that. I mean, this is the big problem with Iran. Iran has lots of centrifuges, and they're producing enriched uranium, and some of it up to 20%. You have to enrich up to greater than 93% to make a weapon. Okay? And they're enriching some to 20% for their quote-unquote research reactor, and nobody likes that because it's not that far from 20% to fully enriched. Enriching up to 5% is not a problem. You can't. 20% is kind of the nominal limit of what people say is not weaponizable, but the reality is you have to be around 93% to really make a weapon. Now there also are laser-based approaches that are being commercialized in the United States, an Australian approach. Okay, so after we've enriched uranium, then we convert it back into a uranium dioxide powder, and then the uranium dioxide powder is compressed into pellets, and there you can see what that pellet looks like. It's bigger than an eraser, but like you see there. Then we have tubes that are made out of a zirconium alloy. It looks just like stainless steel. Zirconium just has a very small neutron absorption cross-section, so it's convenient. And so you have these thin tubes. The pellets go into those tubes. The tubes are about 12 to 13 feet in length. Those tubes can then get strapped together into an assembly here, okay? Now, these are leak tight there. The water is going in between those tubes. So you've got this long assembly, 14 feet in height, and then a number of those are stacked into a right circular cylinder. Okay, so the diameter is maybe 13 feet, the height's about 14 feet. Again, the water flows up around the outside of those and gets heated up around the outside. Okay, power plant construction, as I said before, nuclear power plant, the electrical output of nuclear power plants is really big. And there obviously are economies of scale that have driven the industry to build bigger and bigger designs. So when we look at the General Electric version of this Generation 3 Plus, the passively safe reactor, it's over 1,600 megawatts electrical. It's a lot of energy. And economies of scale, obviously, as far as the power generation costs, it's lower because of these economies of scale. But it introduces a huge problem as far as building a plant in that it's so expensive to buy it. And then, so that has been a major problem. If you walk through a nuclear power plant, it just looks pristine clean. I mean, you go through a coal plant and it's just ugly. I mean, it is ugly. But you go through a nuclear power plant, things are clean, everything is shiny, and there's some of the philosophy there that comes from the nuclear navy of keeping a clean ship. So when you look at a nuclear power plant, you don't see anything that's objectionable. What's coming out that stack there is steam. That's not nothing evil. This is showing as far as nuclear power plant operation. So basically what you have is a control room that you operate the plant with. Looks something like this. You'll typically have like 3 operators in that control room. And then there are maintenance people around the plant that are doing various things. This is with the head off and looking down as we would be refueling, looking through water down on the tops of assemblies there. And this is kind of the range of sizes of reactors today. And then the small modular reactors, less than 300 megawatts each, and basically you would put them together in modules. And mPower has either a 4-pack or a 6-pack of modules that they're thinking about. NuScale, which is a derivative of a design that Oregon State University developed, has 20 modules. I think that's a ridiculous number of modules. Myself, they're too small. And Westinghouse is also a major potential player in this market. But right now, mPower has a big advantage because they won a DOE contract here. So after you've operated the nuclear power plant for 18 months or 2 years, you'll take some of the fuel out and you'll put it into a pool underwater, because it still is radioactive. It particularly shortly after you shut down the reactor and you take that fuel out and you stick it in the pool, it's pretty hot. Then after a year or so, it's decayed down quite a bit relative to what it was when you took it out of there. And so that's pretty much where most of the fuel that's been burned in nuclear power plants is today, although a lot of it also has been taken out of that. After it's been in the pool for about 5 years, then you can put it into dry storage casks. This is a dry storage cask. And here we see dry storage casks on a pad outside there. Okay. So then the idea would be to take them out of the dry storage casks and ship them off to Yucca Mountain, if there were a Yucca Mountain repository, which there isn't today. And we'll talk about that. Okay, so when it's in the pool, there's a vulnerability here. If you lose the water in the pool, particularly right after you've put a load in there, you can have an ugly situation in which you don't really get enough air cooling to cool these zirconium-clad fuel, and you could potentially have what they call a zirconium fire, where the air is actually heating up and oxidizing zirconium, and you could release cesium from that pool. That's why there was so much concern to Fukushima about the spent fuel pool that people thought was empty, which was never empty. It was always full of water. And there's been a lot of concern, a lot done in the United States about this, particularly after 9/11. There was equipment provided to nuclear power plants to make sure that in the event that you had an attack that affected the spent fuel pool, that you would have a pump and ability to pump water in here. And that equipment's called B5B equipment, and I'll explain why. That also could have been used, if they'd had that at Fukushima, they could have also used that to cool the reactors. And one of the things that the industry is doing now is providing equipment that we call flex equipment that isn't actually in the plant, but is located, some of it in adjoining buildings of the plant, that could be taken if you really got to this extreme circumstance where all the various safety systems that we have, redundant, diverse versions of, should fail. Okay, now, as far as Yucca Mountain is concerned, well, let me get into this. So, historically, 4 major issues that nuclear power plants have faced. One is safety, proliferation, waste disposal, and economics, and I'll address each of them at least superficially. I'm going to start out with reactor safety, because that's my area. And what I'm going to show you here is, first of all, recognize that what we have down here are fatalities, and this is a log scale here. Everybody knows what a log scale is, I know. And then this is an exceedance probability. So the way you read this figure is, you go here, and so this is 0.1. This is a frequency of, well, it's, yeah, of 0.1 per year. Okay, so we go over here if we want to see what's the number of fatalities or more that are produced that are from hurricanes once every 10 years. It's 500 or something like that. So once every 10 years, you would expect to see an event that involved 500 or more fatalities from, this was hurricanes. Okay, so that's what it's called, the exceedance frequency. It's on a log scale. And WASH 1400 was a study where Patel was a major player in that study, and it was issued in 1975. And basically, this is 100 nuclear power plants here. This is fatalities that presumably would result from a high exposure to radiation such that you died from radiation sickness within 30 days or so. Okay? Now, the reality is, as we've looked at better and better methods, the likelihood of any fatalities is almost zero of this kind. There's some potential for latent cancer fatalities from exposures that are less than this. But at the time of WASH 1400, this was our assessment. This is 100 nuclear power plants. Here are all natural events that occur in the United States. And here we see like 5 orders of magnitude difference. So relative to natural events, nuclear power, really small contributor to risk. There's a curve that I'm not going to show you that looks just the same for man-caused events like dam failures and stuff like that. Okay, WASH 1400 happened right before 3 Mile Island accident. After the 3 Mile Island accident, there were a number of safety improvements that were made, real safety improvements that were made in plants that makes them much safer than they were pre-TMI. And as I mentioned before, there are going to be some additional changes made relative to Fukushima improvements. So you look at that. Now this is for an average person someplace in the United States. It doesn't say what happens to a person that lives right next door to a nuclear power plant. What's their risk? Here's average. You know, we live 70 miles from any nuclear power plant. Maybe it's a little more. But what if you lived within 1 mile of a nuclear power plant? So the NRC developed some qualitative safety goals and quantitative health objectives, and I'm just going to show you the quantitative health objectives that they established. They wanted to make sure that the risk to somebody who lived right next to a nuclear power plant from that early fatality, that's the kind of fatality I told you about before, where you get an exposure and you die within 30 days or something like that. They wanted that to be insignificant, and they defined insignificant as less than 0.1% of the risk of dying from an accident, car accident, fall in your bathtub, whatever. Okay? And then they also wanted to make sure, as far as the risk of cancer for people living within 10 miles of the plant should be less than 0.1% of the risk of dying from cancer from other causes. So that's how they really define insignificant. That's the objective. So in the late 1980s, we redid WASH 1400 and did some other things better with improved methods and stuff. And this kind of, so there are 5 nuclear power plants we looked at in New Reg 1150. And what we see here is this is this is a slightly different measure. This is individual fatalities per reactor year. Okay? This is the safety goal. So that's your risk of dying, and that's 0.1% of your risk of dying from accidents. Okay, so that's what the safety goal is. There's a detailed uncertainty analysis done in New Reg 1150. The uncertainties are large. This is the 5th percentile at the bottom. I'm sorry, yeah, 95th percentile is the top. Mean value of the uncertainty is that bar. Median value is this bar over there. So if we compare that with safety goals, what we see, and this is for the individual fatalities, is latent cancer, this is early fatalities, latent cancer fatalities, what we see is large margin to the goal. Okay, so what that means is that, and remember, the goal is 0.1%. So what we're seeing here is something like your risk is like 1 out of 100,000 relative to other risks that you face. So if you say, gee, there's some property that's right next door to a nuclear power plant, 1.5 miles from a nuclear power plant, should I worry about that? Should I not buy that because of that risk? And the reality is, you would be ridiculous to worry about that risk, even if we're wrong by a big margin here. And we've taken a lot into those uncertainties. The human health risk is really small to people. And there's nothing about that really is affected by Fukushima. At Fukushima, nobody, even, so this includes the frequency of core damage events. Even with conditional that Fukushima actually happened, there's nobody that got any significant radiation exposure, and nobody that will get a significant radiation exposure other than really low probabilities of increasing their potential to get cancer. Less than 1% of their existing probability, which is 40% of people are diagnosed with cancer. So even the worst exposed people are going to have negligible health effects as a result of Fukushima. Doesn't mean there isn't a huge societal cost, and that's what we're going to talk about next, or almost next. So if we look at societal risks as opposed to individual health risks, and I'll give you a better feeling as to what I mean by that, the NRC also had a qualitative safety goal related to societal risk, but they never developed any quantitative measures to compare against that with. And that's something that I've been looking at over the last year intensively with a graduate student. I'll show you some of our results. This first one is just a comparison with other forms of electricity generation. So part of the NRC's qualitative goal was that the risk for nuclear power plants should be comparable to or less than the risk of other forms of producing electricity. The Paul Scherrer Institute in Europe done a lot of work on this, looking at the entire life cycle. That is from the time you're mining and things like coal or drilling for oil and stuff like that. What are the risks of, and here it's years of life lost is what their measure, and it's on a per common amount of energy produced. And so what we see is, not surprisingly, that these are all small risks, okay? And that nuclear is comparable to or less than things like wind, hydro, solar. Okay. Now the part that I've really been looking at, though, is a question of land contamination and what are the economic implications of land contamination. And there are also other societal implications in terms of people that are forced to move out of their houses, that may never get to go back to an ancestral home or things like that, that are difficult to monetize. So what I wanted to look at was, what are the really catastrophic things that happen that really have a major impact on our economy? And And I wanted to monetize those. I had to put them in a common form. Some people don't like monetizing deaths and stuff like that, but I did. And so I used $5 million per life. It's not a bad number when you look at this. And I looked at various things. Well, the big event is wars. Now, I just looked at the United States, and our biggest war is the Civil War. And this blue curve is wars, and in that point right there, that's 600,000 people that died. Now, if you look worldwide at wars, and you look at the number of people that died in World War II, these numbers are way over here. So there is a potential for wars to lead to much bigger. And in fact, even in 1962, there was a threat during the Cuban Missile Crisis where we were maybe this close to a nuclear exchange that could have led to catastrophic loss of life, maybe even global nuclear winter. Nuclear winter is, people don't talk about that so much like they used to, because people are under the impression that we've kind of done away with the risk of a global nuclear warfare, whereas the reality is that potential is still there. Okay, then the next thing I looked at here are epidemics. My wife had a grandfather that died in 1919 from Spanish flu, and this is kind of epidemics that have occurred in the United States, that risk. Again, this is where I'm looking. Again, I'm looking here, constant cents or equivalent dollars. This again is this exceedance frequency, where you go across here, say at this frequency, what we see is that you have the potential for $2 billion loss or greater per year. Okay? So, and then I put in recessions there, and then recessions was the green. I was really big on recessions because we're in such a nasty recession. And then I looked at floods, earthquakes, all this other kind of stuff. And so in my view of the world, then this top is, that's the risk that we face in the United States on a daily basis based upon history over the last 200 years, sometimes less than 200 years. But that's the risk that we have of a catastrophic event that would have consequences of a certain amount or greater. Okay? Now, again, when you think about the potential for epidemics, the potential for warfare, this curve really does go out here. And one of the things that's kind of surprising to me is how relatively flat this curve is on a log-log scale. I would have kind of expected it to drop off much quicker. And the reality is there's some stuff out here that it's kind of scary. But in any event, so that's what my goal, that's what I see as the background. And then I won't go into how I did the nuclear power plant, but based upon New Reg 1150, some recent stuff that's been done in the Sandia thing, I came up with a kind of an uncertainty band, what I see the societal risk of land contamination. This is just release of cesium from the plant, contamination of land. Cesium-137 happens to be the really bad actor as far as land contamination is concerned. And loss of productivity on that land. This particular curve, I think, has a little bit of decontamination cost in it as well. And I've done sensitivity studies on that. So anyway, now, the NRC doesn't have a quantitative goal, but if you looked at the quantitative goals that they had, other things like 0.1%, then this would be 0.1% of that background risk, okay? So what this says to me, and I'm not sure the rest of the world agrees with me yet, but it says to me is, we really looked at risk of nuclear power plants totally inverted, that the real risk isn't of dying from an accident, either from latent cancer fatalities. It's not that individual health risk. The real risk is that you could contaminate a lot of land. People might not be able to move back into that land. You'd lose the value. French have done some similar things, not within risk space, but just looking at, and they use much bigger conversion factors than I did, because they worried about things like what happens to my vineyards and my wine thing and stuff like that. And they get tremendously big dollars lost due to land contamination. Okay? So the NRC right now is trying to decide whether they're going to do anything at all related to this societal risk. And I think that the reality is this is the dominant risk. This is the risk that a country is going to look at nuclear power, say, and like Belgium, looking at that and say, geez, I could have an accident where there is no habitable land anywhere in the country of Belgium, or I've contaminated my neighbor pretty severely, this kind of stuff. So particularly for a small country, you might ask yourself twice, am I going to have nuclear power? Okay? Now, but of course the nice thing is, nobody dies here. This is really more inconvenience and some shock to the society. But these kind of things happen all the time, as we see here. 10 billion, 50 billion, yeah.
So we're not just talking about the inability to grow crops and grow things. You're saying that just completely uninhabitable by humans? Well,
first of all, you could always decontaminate. It's just a matter of the cost. Okay? And basically what I'm assuming here is that, in this particular one, that the EPA criterion is that if you're going to be exposed to greater than 2 rem of dose, and we'll probably get into that, in the first year, you have to relocate people. So that's basically what this is. Now, 2 rem, the reality is you can live in 2 rem per year with almost no impact on your health. But, and some of it gets into uncertainties about low levels. Okay, let me continue because I don't want to totally run out of time here. As far as proliferation of nuclear weapons are concerned, nobody uses their commercial fuel cycle to produce weapons. They use other things if they're going to become a weapon state. If you're a signatory to the Non-Proliferation Treaty, like most countries are, we can control that. The real problem is with countries like Iran and North Korea that aren't signatories and don't have inspectors. That's a major problem, but it doesn't really relate to nuclear power plants. This cancellation of Yucca Mountain was really purely political. I was on the no action alternative. For every time you do an environmental impact statement, you have to look at, what if I don't do anything? And I was on the committee that advised the group that did the no action alternative, which is kind of what we've done, relative to Yucca Mountain. And basically, there's an uncertainty analysis that's done for Yucca Mountain that had been presented to the NRC, that NRC was about to review when Yucca Mountain got canceled. And that was a strong case. And we have safety criteria for waste disposal sites that are just ridiculous in terms of, you look 10,000, 100,000 years in the future and require really trivial exposures to the maximally exposed individual. They're just ridiculous. There's no other technology where we think beyond 50 years in the future. And look at global warming and the lack of people looking to the future. The criteria are ridiculously restrictive, and yet they're and yet they can meet that with a significant margin. One of the things people worry about is the transportation of waste from the nuclear power plant site out to wherever the repository would be, and the shipping casks that are used for that, or would be used for that, are really robust. This just shows you an example of a truck going at 60 miles an hour into a solid thing with a shipping cask on it, and you'll see what happens to that shipping cask there, which is not much, and it's scarcely dented. The other thing is, people think, what if you had a breach in that shipping cask? And the reality is, you've got solid fuel in there. Unless you get it really hot, there's nothing that's going to force radionuclides to be released from there. And this is, when they get shipped, they've been out of the reactor for an extended period of time. As far as economics are concerned, the big issue is this upfront cost of a large plant. There's also a lack of confidence by the lenders because of the history after 3 Mile Island, when there were a number of nuclear power plants that were in the licensing queue, and they got delayed as much as 12 years as a result of licensing delays. And that means a lot of money, because remember, all that time you've got all this money you've invested and you're not getting any money back. So that's why loan guarantees are important, is that the lenders put a huge premium on their loans for nuclear power plants. So the government for these first plants that are out there has provided a loan guarantee. Now, a loan guarantee makes money for the government unless the program defaults. Okay? And there was a lot of argument. The utilities felt that the government accounting office was holding them hostage with high interest rates on the loan guarantees. But in any event, the National Academy of Sciences has done a study of America's energy future, and if you guys haven't looked at that, you certainly ought to look at that report. And basically what it shows is that the cost of new nuclear plants without loan guarantees in an area of 8 to 13 cents per kilowatt hour. If you have loan guarantees, 6 to 8 cents per kilowatt hour. Coal, 5 to 9 cents per kilowatt hour without carbon capture. With carbon capture, if you can do it, gets really expensive. Natural gas, at the low price, nothing competes with natural gas right now. As far as wind is concerned, there is some wind power that's quite economic, but most of it isn't really that economic. We give a 2 cents per kilowatt hour subsidy for that, and that's probably worth it. But wind can never be the substantial source because it varies, and we don't have a good way to store electricity. So you really need something that is a major source, a base load for production. Solar photovoltaic, they show, is 15 to 30 cents per kilowatt hour, obviously very dependent upon where you are. And the AEP did an estimate for themselves that came up with 80 cents per kilowatt hour in this area here. I did an assessment based upon a calculator that the National Renewable Energy Laboratory had, where you could put in the latitude and make an estimate. That's what I got out of that calculator. So the cost here is really extremely low. So there really aren't a lot. That doesn't mean that there aren't places for all of these. So why does it matter? Global warming's real. The impact of our selfishness today is going to be felt on future generations. The natural resources of the world are really limited. And people talk, oh, there's 100 years of natural gas, as if 100 years is as long as civilization is going to live. Wait until you've lived as long as I have. And you live, my wife's mother lived to 100 years old. I mean, and the time goes by like nothing. And I'm worried really about our children and our grandchildren, about energy resources. You look at things like availability of food supply, availability of fresh water. All of these things really depend upon energy, and inexpensive energy is really important. So I think we really need a balanced policy that includes renewables. So my final comments: nuclear gets a bad rap. They're really, really safe, economic on a level playing field, very minor environmental impact. Issues delaying geologic repository, political, not technical. I think the unrecognized risk is the societal risk of land contamination. And the post-Fukushima plant modifications are going to help. But really, if we went to these Generation 3+ reactors, they have another level of safety beyond the safety of plants today. That's it. Questions? Yeah.
When you were talking about Iran and 5% is an acceptable number, and they're at 20%.
No. So basically, most of the enrichment they've done has been less than 5%, and related to providing the fuel supply for their reactor, their commercial reactor that the Russians have provided. That's legitimate. They have a research reactor, and the world allows 20% enrichment on research reactors. We still have some reactors in the United States that are fully enriched, even at MIT, but because they've had a problem getting the kind of performance that they really want. But in any event, I'm sorry, so back on that question.
Well, my question is just, if they have to be upwards of 90% to make a weapon, why is the difference between 5 and 20% such a big deal if they have to get all the way to...
It just puts you that much closer. And the reality is, as you get closer and closer to highly enriched, it takes more and more energy to do it. So even going from 20% to 93% requires a lot of energy, probably as much energy as it took to go from 5% to 20%. So it takes time, because
But to get from 5 to 20% is the same amount of energy you get from 20 to.
probably. I mean, the energy level goes up of increasing the enrichment as you get closer and closer to highly enriched. But I think the reality is nobody knows where they really are. You know, clearly the Israelis think they're closer than we think they are, but I don't think we have. I mean, based upon Iraq and our level of intelligence about where Iraq was, I would assume that our level of intelligence on Iran is limited too. Yeah.
So is the passive cooling all airflow, ventilation?
No, it's a number of different things. That's part. So as far as the reactors is concerned, you don't need pumping power to pump the water around. It just occurs by natural circulation. Okay, so a lot of it is that way. If you have a pipe break, and they've cut down on the number of pipes in these plants, you have gravity drain. Okay, and then as far as the ultimate heat sink is concerned, then you would have some natural convection that would take you to air cooling along the lines that you had there. So it all involves pretty much gravity and natural circulation in one form or the other. And one of the issues there is that although you can't build in as much margin with those natural things, and you always worry a little bit about whether you fully have understood it, because those tend to be tricky as to whether, when will natural flow be established and that kind of stuff. So I really like systems that have both active systems and passive systems. But the passive systems in these plants they're backup final systems. Anything else? Yes.
With the next gen reactors and like Gen 4 reactors and so forth, what is the longevity of nuclear? Like how long are we looking at powering our needs?
Well, the big switch over is to breeders. Okay, so they're kind of three levels. The first is just burning stuff and throwing it away. And one of the things I liked about the fact we didn't do Yucca Mountain is that it actually enables us to take that and eventually reprocess it. Yucca Mountain would have allowed us to recover in 100 years, for up to 100 years or something like that. But in any event, so the big changeovers are like to breeder reactors, where you can take really much bigger use of that full amount of U-238. And then you've got this huge thorium supply too, where you can convert thorium to uranium-233. And there's some really big advocates of thorium reactors. They're not going to happen in the real near future, in all honesty. But so that's a huge uranium supply, huge thorium supply, and that's many centuries that we're talking about there.
Okay.
I guess we probably ought to call it quits. People have to go on.
All right.
Any other questions? No?
Thanks so much. That was great. Ooh.
Well, of course, I tried to pack more in there than I could.
I was thinking, this is better than a TV show. This is fascinating.
Oh, and you would like, shall I just leave that guy on there?
Yeah, sure.
Okay. That isn't what I really called it. I'll get rid of the truck and the train. I didn't kill him.
Yeah.
Here's my email. Can you send me information on that group you were talking
Yeah,
about?
yeah,
2 weeks ago?
definitely.
Yeah, I tried to get you. Did you come call last week?
Last week,
Beautiful.
no. No, I think one day